Alright, in this video today, I'm going to be teaching you how to subnet IPv4 addresses. This is probably going to be one of my longest videos that I'm going to make. I'm going to teach you how to subnet from start to finish. So, I am your host, CCMP Seth. So, let's get into it. So, we're going to start with IPv4, and here are some terms that we are going to define throughout this whole video or today's objective. So we're going to define terms like what the host is, what the IPv4 network means, IP class, IP address, host address, all these things. So don't get overwhelmed with all of these terms right here. If you don't know it, it's okay because I'm going to go through it with you. All right. So let's get into it. So what is an IP address? Well, IP stands for Internet Protocol, and it is just a numerical number assigned to a computer on the network. That's how the internet works, that's how they talk to each other, and it is constructed of 32 binary bits. All right, bits are represented with ones and zeros, and the way a computer or a router sees data, it just looks like this. Just a whole bunch of ones and zeros, 1100110001, and based on whatever these strings of numbers are, a computer or a router knows exactly what that means. So we have to break things down into bits or binary digits, and these are all ones and zeros. All right. An IPv4 address is comprised of a network portion followed by a host portion. So we'll further define what is the network portion of an IP address and then what is the host portion. All right. So clear that off. Next slide. Some things you need to be aware of for IP addresses is the class. Now, the usable IP addresses that you could be assigned to hosts, they could either be a a class A address, a class B, or a class C. So what I mean by host is you on your computer right now, if you're hooked up to the internet, you will have one of these addresses. You will either have a class A, class B, or a class C. Now, if you're on your home computer sitting behind your own home router, more than likely you have a Class C private address, but the actual public address that you were assigned by your ISP will probably be something of a Class B or a Class A right there. So, but that goes into NAT, and that's a whole nother video if I plan on doing it. But right now I'm just trying to teach subnetting. So, all right, so let's see here. Class A has one octet, which is 8 bits assigned to the network portion, and the remaining 3 octets, which are 24 bits, they are assigned to the host. Class B is the first 2 octets, and the last 2 octets are used for host. Class C is the first 3 octets are used for the network portion, and the last octet is assigned to the host. All right. So here's another picture on how it can be represented. See here, the first octet, network. Last 3 octets, hosts, so on and so forth. And in America, this is assigned, or the way you would get your network number, it's assigned by ARIN, the American Registry for Internet Numbers. So if we have a number in the first octet and all host portions right here are set to 0, that would be defined as a classful network. Now, what determines an IP address from Class A to Class B? That's further down in a couple slides. But just know that all zeros in the host field of a certain address, that is the classful network. All right. So just think about that right now, and then I'm going to continue on with the slides, and hopefully it'll click. All right. Because teaching subnetting in a short amount of time, it's very tough. All right. So if we have an address of 9.0.0.0, that is the classful network address. 192.168.1.0, like we see here. This is a Class C address, and the first 3 octets is used for the network, and this last portion right here is used for the host. All right, so on and so forth. So you get to see here Class B, Class C. All right. So here is a slide showing if we were to put numbers here. If all these numbers right here were filled in, now based on whatever this number is, that will determine if it's a Class A, Class B, or Class C address. So even though there are numbers filled in right here, this is the host portion of an IPv4 address, but at the classful network, it is just 85.0.0.0. So that is a classful network. Same thing with Class B. The first 2 octets are used for the network. All zeros in the host portion, that makes it the classful address. So classful address for this Class B would be 168.65.0.0. Right? Same thing with Class C. Those first 3 octets, that's the classful network. Network and host field, see? So this is a host address right there. So how do we know, based on the numbers of an address, if it is a Class B, Class C, or a Class A address? Well, here it is right here. If the first octet begins with a 1 to 126, that is a Class A address used for hosts. If you see a 128 to 191, automatically Class B. Class C, 192 to 223. These other addresses right here, Class D and Class E, they're used for multicast and experimental networks, but that cannot be used on the internet by a host. All right, so there it is. Computers on the network can only be addressed using these addresses right there. So for you to learn subnetting, I suggest that you memorize these numbers right here. So when you subnet, you can automatically know if it's a Class A, Class B, or Class C, and based on that, there is a default subnet mask attached to it. All right? All right. So here are some reserved addresses used in IPv4. We have the 10 network. So everything that begins with 10, that is a private address space for IPv4. Also, the 127 network is also reserved. You might know the loopback address of a computer, 127.0.0.1. That is the loopback address. Let me put a 1 there. That you could ping it, and this whole address space right here is reserved. Class B, it is 172.16.0.0 all the way to 172.31.255.255. And then Class C, anything that starts with a 192.168, bam, automatically reserved, not allowed to be on the internet. 9 times out of 10, this is probably your personal address space for your home router. If you have like I guess a big consumer router for your home network, it may start with 10. But majority of them will start off with 192.168.0. something or 1. something. But, you know. So, all right. All right. So now let's get into IPv4 and the actual binary system. And I'll teach you what a binary bit is, 0 and 1, and actually how to count in binary. So let's move on to the next slide. And in here, in the binary system, every binary digit has 2 values. It is either a 1 or 0. That is it. Basically, is that bit turned on or is that bit turned off? All right. Now, we care about all bits, zeros and ones, but we want to pay more attention to the 1 bits. all right, because this will actually give a value. So each value is a binary digit or a bit for short, and if we see a string of binary numbers like this actually means something to the host router, or I'm sorry, the host computer or a router. Let's see, each bits together make a unit called a byte. You may have heard that. So 8 bits are in a byte, and an IP address, bytes are called octets. So a group of 8 bits equals an octet. So when I say what is in the third octet, I'm talking about the third, let's say it's 192.168.1.50. Oh, that's a 60. When I say I'm talking about the third octet, I'm talking about the third string of bits. Okay? So here in the decimal system, each place value is a power of 10. So this is actually what it looks like. 10 to the power of 0, this is the ones place. 10 to the power of 1, there's the tens place. So on and so forth. So when we see a string of numbers like this, we read it as 2,342. Binary is a little bit different, and it's not based on the tens or the power of tens, but it is based on the power of 2. So you see here, 2 to the power of 0 equals 1, 2 to the power of 1 equals 2, then 4, 8, 16. So you kind of get the gist of it. Basically, you start off with 1, and then you multiply it by 2 every time. And after you multiply it by 2 every time, you can't go wrong with what that value means in that place. So if we saw a string of 8 digits, or I'm sorry, 8 bits in an octet, let's say it looked like this: 11001111. Now, how do we convert that to the decimal system? Well, based on where it is in that octet, you look at the place value. So this 1 equals 128. This second one equals 64. These zeros are turned off, so we don't care about it, so just X that out. This value is turned on because it has a 1, so that means 8, 4, 2, and 1. So you add that up. So 128, 64, 8, what else we got? 4, 2, and then 1. So 128 plus 64 equals 192, plus 8 equals 200, 204, 206, and then 207. So that is how we get 207 when we're trying to convert binary digits into a numbering. So that is how we convert binary into the decimal system. All right. So what's next? 32 bits of an IP address are grouped into 4 bytes. I kind of already mentioned that. So when we look at an address, an IPv4 address, we will get a string of ones and zeros. They may be overwhelming, but just break that down into octets or a string of 8 bits, and then you will get a value. All right. So remember, in 8 bits, the first digit is worth a value of 128. The last digit is 1. And then you just simply multiply by 2 every single time. And see if I could write it in. I'm probably going to run out of room. 16, 32, and then 64. So these two values actually fit in right there. And then based on if it's a 1 or 0, then you just add it up. Ones we care about, zeros we do not. So let's see what it turns out to be. If you want to actually go ahead and figure this out right now, I'll wait a couple seconds. You could pause the video. Maybe I'll play a little music actually. Let's see if I can play some music while you do this. Uh, do this, and then I'll go to the next slide and I'll reveal the answer. All right, that was 10 seconds. So let's see what we got. 169, 199, 69, and 137. I hope you got that. I won't go. Let's see right here. So that value is turned on. That one, and that one. So that means 128 plus 32 plus what is that? 16, 8, 4, 2, and 1. So 128 plus 32 equals 160 plus 8, 168, 169. Bam. Uh, these 5 values. So 128, 64. What is that? 4, 2, and 1. So that is 192, 196, 198, 199. Bam. And then we got a 64. What is that? The 4 value. And then 1. 64 plus 4 equals 68 plus 1 equals 69. And the last one. 128 plus 248 plus 8. And then 1. 128 plus 8 is 136 plus 1 is 137. All right, bam, there we go. Sweet. So there you go. We just converted a binary IP address into something that we as humans can actually interpret. So sweet. So I have some exercises that I've created. I'll see if I could post it somewhere so you could actually practice, and now would be the time to complete it. Yeah, so I'll see if I could find a place to post it. It'll probably be on some public media share website or something, and you can practice. Yeah, you can practice these. So I want everyone to be proficient in subnetting. So yeah, I like teaching. So after you complete exercise 1, that's like the basis, the foundation on actually trying to subnet. So you need to know what a string of bits means. So once you are very good at that and you can, convert binary to dotted decimal, boom, you're good to go. Now we're actually going to get into IPv4 subnetting. Very, very exciting. So what is subnetting? Well, here is what I have defined in it. Creating multiple subnetworks that contain a smaller number of usable IP addresses. So what that actually means is, if we were given, let's say, a Class A address, then that is our whole entire network, which means all devices are going to be in the same broadcast domain. So if I was to send a broadcast message out like a DHCP request, or I'm sorry, a DHCP discover request, which is where you get an IP address from a server that hands out IP addresses, that is broadcasted throughout the entire network. So if we have a full network like a class A and we didn't subnet, then that means all machines on that network have to listen to that address, which we don't want. So we want to break them up into smaller subnets and put like devices together. Like all the hosts on a network, they should be in one network. All printers on a network should be on their own network. All IP phones on their own network, so on and so forth. So this is why we subnet. One thing to point out when you do subnet is we lose IP addresses every time we create a subnet. It says we lose 2. That is right, because with every subnetwork, or I should say network in general, there is a network ID and a broadcast address. All right, and Those cannot be assigned to hosts. Those are reserved for every network. So let's just remember, every time we create a new subnet, we lose 2 IP addresses for the hosts. Okay? Right. Like I mentioned before, an IP address has 2 parts. We have a network number and a host number. Some people may refer to it as a network ID or a network field. You also may hear it the host number being a host field. Whatever the term is, just make sure the person you're talking to, you guys can be on the same page, right? So some people may know interface VLANs as just interface VLANs, but if you're talking to someone who has no, I guess, practical knowledge, I guess, it's all theory, we know it as SVIs, switch virtual interfaces. So you just have to know who you're talking to and find that common ground. So that's why I put these here. Network number, network ID, or the network field possibly could mean the same thing. So the network ID, the class full identifier of a network. So when I say network ID, I'm talking about the class full identifier of that network. I like to say subnet ID, so I know who I'm talking to, or at least I know that what I'm talking about is a subnetted network. So when I say network ID, I'm talking about classical network. If I say subnet ID, then I'm talking about an actual subnet ID. But depending on who you're talking to, that could mean the same thing though. So majority of the time, everything is subnetted in the world. Mainly, you could even break down a Class C address even further, but so when you're talking to another networking technician, they could be like, "Oh, what's the network ID of this address?" They're more than likely talking about the subnet ID, but just be like, "All right, subnet ID or the classful network ID." You should probably say classful network ID, just so they're talking about big picture here. So let's see, what else do we have? All zeros in the host portion are in the address. So remember how we had, the network portion and then everything else, all those other octets, they were all host. H. That means all zeros in here, and we just have the network number. That would be the network ID. All right. Network IDs cannot be used as an address for any device that is attached to the network. That's right. If you were to try to configure that on any device, it would throw you an error and say that won't work, whether it's on a Windows machine or even a router's interface. Like, nope, that doesn't work. All right. So with Class A, only the first octet we care about. The other 3 octets, they're all zeros. Class B, we care about the first 2 octets. The last 2 octets, all zeros. Class C, we care about the first 3 octets. They are known, that is the network ID, and that last octet is used for the host. All right. So with that being said, let's actually do some little practice questions. All right. So let's see here. Let's identify the network field. So based on this address, what is the network field of it? So we see this is a 199.4.6.36.5. All right. So remember a couple slides back, based on what this first number is in the octet, it will define if it is a Class B, Class C, or a Class A address. So 199, what do you guys think that is? You think it's a Class A, B, or C? Let's see here. It is a Class C, and that being said, the Class C, that is the network field, the first 3 octets. All right. So pause the video if you want to do this on your own, but I'm just going to go through it right now. All right. So this second IP address, what is the network field? The first one, the first octet, 111, because it's a class A. Let's go to number 3, number 7, because again, class A, first octet. Fourth one, it's going to be the first 3 octets because it's a class C. Number 5, first 3 octets again, class C. Number 6, the first 2 because it is a class B. All right, good job. So let's see here. Can we change this part of the address to subnet? What do you guys think? No, you cannot change this because that, based on it being the classical network, you cannot go beyond those networking bits. So when we subnet, we actually take those host bits in the host field and we turn those host bits into networking bits. We can never turn our original class A, class B, and class C networking bits into host bits. You cannot do that. All right, not when it comes to um, uh, assigning an IP address to a host. Okay. So that being said, what is the let's identify the host field now based on if it is a class A, class B, or class C address. All right. Pause this video if you want to write it down and practice. If not, I'm going straight through it right now. So what is the host field for this first address right here? Host field is the 9 because that is a class C address, and the host field is the last octet. Number 2, it is the last 2 because it is a class B. Number 3, it is the last 3 octets because it's class A. Number 4, it is a class C again, so the last octet. Last 3 octets for number 5 because it's class A. And last one is a class B, and that is the last 2 octets. Now, can we change this portion of the address to subnet? What do you guys think? Yes, you can, because we are borrowing those host bits and turning them into networking bits. We are allowed to do that in IPv4. You cannot change the original networking bits to make you cannot use it to subnet. We could only turn host bits into networking bits, okay? All right. So now that we've identified the networking field, networking portion, and the host portion of an IP address, the next thing that we need to identify is the subnet mask. Now, subnet mask is pretty much everything to an IP address. Without it, it doesn't mean anything. I just have an address. So we need to know what that subnet mask is. So subnet mask corresponds to an IP address, and it goes together with an IP address like peas and carrots. All right, you can't have one without the other. Peas and carrots. All right. The subnet mask is just like an IP address, has 32 bits, but has a different meaning. So a 1 bit in the subnet mask means that the corresponding bit in the IP address should be read as a networking bit. All right. So remember how we had the network portion of an IP address based on class A, B, or C. That is represented in the subnet mask as 1. All zeros in the subnet mask means that the corresponding bit in the IP address should be read as a host bit. All right. So let me give you an example right here. So let's say we have 10.0.0.1, that's in the IP address, and let's give it the default mask of 255.0.0.0. We know that this is the default mask of the 10 network because remember the first octet in a class A address, that is the whole networking field. All right. So that means, how do we draw 10? 128, 64, 32, 16. 8. That's a 1 bit. 4, 2, and 0. All right. So that is what 10 looks like in binary. And that means all of these, this is the subnet mask right here, all of that is turned on, and these are identified as the network portion. All right. Then everything else we don't care about, since these are all zeros in the subnet mask. 0, 0, 0, 0. That means that the corresponding bit up here, which coincidentally are all zeros, because that's how you make zeros in binary from dotted decimal. Let's see, 1, 2, 3, 4, 5, 6, 7, 8. Is there 4? One more. That all of these, since there's zeros in the subnet mask, that is the host portion of it. All right. All right. So, like I said, subnet mask is also another 32-bit value, and its job is to tell the routers and humans which bits of the IP address are network and which bits are used for hosts. All right. So based on this, we could clearly see which of these bits are used for the network. Remember, go back to what I said. All ones in the subnet mask means that the corresponding bit is going to be used as the network. So the network portion stops right there and includes the first 2 octets. And then we just convert these into dotted decimal, which will give us a value, but that's it. And then the last 2 octets are used for host. So here the first 16 bits of the mask are set to 1, thus the first 16 bits of the IP address is the network number. Okay. All right. So there it is. Kind of like how I just highlighted, the mask shows that the first 2 octets refer to the network number. Sweet. Network field, host field. How do we know that? Based on the subnet mask. Sweet. All right. Now, what about this one? No, same thing. Mask again, all ones. Network field, host field. All right. I don't want to beat that into you, but it's just easy. What is the network field of this address? Well, it stops at the 3rd octet because these ones are there. Plain and simple. All right. Now, here's the classful boundary or the classful networks for Class A's, Class B's, and Class C's. So we know that the first octet in a Class A is the network portion, so that means that is all 255s. Reason why it's all 255s, if you add up 1, 2, 3, 4, 5, 6, 7, 8. If you add up 8 bits and they're all turned on, the highest value you can get is 255. Okay, so that's why when all networking bits are turned on, when they're all ones, everything in the octet is 255. Bam, 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 bam. All right, so when we're on the phone or if we're talking to other networking technicians and then we're like, hey, what's the subnet mask for this IP address? And you look it up and be like, all right, it's 255.255.248. It's like, man, that is a lot of 255s. So they have this CIDR notation or called slash notation that we can refer to make the subnet mask a little bit easier. So we could say a /8 for a Class A, the classful network. Or we could say a /16 or a /24 based on if it's a Class B or Class C. Now what that means is, if I say a /8, that means 8 bits in the networking field. /16, 16 bits in the networking field. Because remember, each octet has 8 bits. All right. Now, what happens if I said, all right, blah, 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 blah IP address, and then the subnet mask is a /18? Oh, no. What does that mean? That means that there are 18 ones in the subnet mask. So we already know that there are 8 bits per octet. So 8 here, 8 here. Now that turns out to be 16, so that means there has to be 2 more bits turned on. And since this is a 1 in the subnet mask, that means that we have now turned those bits into a network bit, or those bits into networking bits. So one way to refer to those extra bits is we could break down our network and host fields into another subnet field. All right. So we need to break up networks into smaller pieces and the classable boundaries. So I guess this was formalized in 1985, probably, maybe. Um, but yes, we need to break our full Class A, Class B, and Class Cs into smaller networks so we could use it as efficiently as possible. All right. So here it says what happened to the host field. Well, this is a 128.11, so we automatically already know that this is a Class B network or a Class B address, and the first 2 octets are our network field. And by default, the last 2 are used for our host. But what happens if we borrow some bits from the host and turn them into networking bits? So now we have our normal networking bits, and I like to say subnet bits, so we can say subnet bits, SN, sure, subnet bits, and then we actually have our host bits. So remember before, like I said, we cannot touch our networking bits. We cannot use those bits to be used for subnetting, but we can borrow host bits and turn them into subnet bits to actually subnet. Okay? All right. So 8 bits in the subnet field equals 2 to the 8th, because if we use this formula, 8 bits, you just kind of just add that to the power of 2, and that gives us 256 possible subnets. All right. Now 8 bits in the host field will give us 256 IP addresses. Now when we get into further subnetting, we know that we can't have 256 addresses assigned to a host. We actually have 254. It's because of the network ID or the subnet ID and the broadcast address. All right, so I'll get further into that. All right, so if we didn't subnet, we would have had 65,536 IP addresses. Why? Because if we had 2 to the 16th power, because we had 8 and 8 bits used as the host, that actually turns into that number right there. So that means we would have had one network that had 65,000 IP addresses in this broadcast domain. That is just too much to handle. So we just break it down into smaller networks, 256 subnets, and 256 IP addresses per subnet. All right? Good, 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 good. So we're getting there. We're learning a lot about IP addresses and subnet masks and Class A and Class B addresses. Now we could finally calculate subnet IDs. All right. So now we're actually going to get into subnetting with equal hosts per subnets. All right. So let's say we got this address 192.168.1.1/27. What we know already right off the bat is since it starts with a 192, what does that mean? The first 3 octets are used as the network. We cannot touch that. That is, we already know, it's a Class C, right? Boom, right off the bat. So when we calculate subnet IDs, in IPv6, what we want to do is first find out what the class is. Bam, class C. Then what we need to do is find out what the subnet mask is. We should know that by default it is a /24 because it's a class C, but we were given a /27. So what does that mean? So we need to identify that. /27 means 27 bits in the subnet mask. You could write that out in binary, and we already know that this is 255, 255, 255, and then we have these bits turned on. You just add that up. 128. No, go back. 128, 64, and 32. Add that up equals 224. So these are the first steps. Determine the class, and then identify what the subnet ID is. Next, let me clear my screen here. Determine which octet we stop borrowing bits from the host field, and this will give us our rotator or magic number. Alright, so that being said, we already know that the first 3 octets are used for networking bits, and we cannot touch that. But we borrowed host bits and turned them into networking bits. So we find out where we stop borrowing bits, which is in the 4th octet, which is right here. And this is where we start rotating this number that we will find. This is our magic number, or our rotator, but we rotate in that octet. All right. Regardless if this was a class C, regardless if it's a class C, let's say this, let me use another color here. Get rid of that. Let's say, you know what, just get rid of all that. Let's say it was a 191. Now that means that is a class B, and the first 2 octets are used for networking bits. But we borrowed bits all the way into the 4th octet. So we're actually focusing on the 4th octet, even though we've borrowed bits way beyond the 3rd octet. So, yeah. So wherever we stop borrowing bits, that is the octet that we want to focus on. So we're focused right now on this 4th octet. So let's go back to our original value. Hope I don't confuse you guys. Let's go back to our original value and draw our classful boundary right there, which is the 3rd octet because we're using a class C. And know that we are in the 4th octet and that's where we're rotating. So we draw these numbers, or we use these binary bits, and we put it to our binary chart. So this is our chart. Remember, all the place values of our binary bits. 4, 2, 1, so on and so forth. So we take this chunk right here and apply it to our chart. So we look at where we stop borrowing that host bit, and we kind of circle it. We take note of it because this 1, since it is the last bit that we borrowed, our rotator now, our magic number, is 32. So it says where the last bit lies, the corresponding number becomes the magic number. All right, cool. Now, what do we do with this magic number? That's a good one. We start using our magic number and start at the classful address, and this is how we calculate subnet IDs. All right, so our classful address for a class C is 192.168.1.0, and our magic number is 32. So what we do is we start at 0 and we rotate by 32. 0 plus 32 equals 32. 32 plus 32 equals 64. 64 plus 32, 96, so on and so forth. So what that means is the first subnet that we have created has an IP address that starts from 0 all the way to 31. That is what this first subnet represents, or the first subnetwork. Then the next network that starts will start with 32, and it goes all the way up to 63. All right, you see that? And then you just keep going to 95. And notice 0 to 31, that gives us 32 addresses because 0 is an actual number, so that number counts. So that is how we calculate subnet IDs. All right. So if you keep going, and let's say we get to 224, we add 32. What does that equal? 256. Is that a valid subnet? Let's see, I have something up here. Why can't we have a subnet of 192.168.1.256? Well, 255 is the limit and 256 is invalid, and you have to rotate to the next octet, which you cannot do because you do not own the next classful IP address. So you have to know where your boundary lies when you start calculating subnet IDs. Since we have a class C address, remember the first 3 octets is what we care about, and that's what we own. Do we own, well, here it is. Do we own 192.168.2.0? Not necessarily, because we have one class C address, so you have to be aware of that. So let me go back a slide, let me clear this off, and let me make sure that I really hammer in our rotator right here. When we have our subnet mask, draw it out in binary, and then the last bit where we stop borrowing, or the last octet where we stop borrowing bits, draw it out with our number. So we have 3 bits right here. Apply that to our chart, and that is our rotating number. All right, and that is how we get our magic number, and we start our rotation. And that is how you calculate subnet IDs. All right. So with that being said, we have exercises to do. Again, once I upload it, you guys can download it and complete these exercises for practice. And then we can move on to actually calculate subnets with a requirement. Right? So what I mean by calculate subnetting with requirements is, let's say we were given a Class C address, a public one, not a 192.168.1, but let's say a 192.170 address, right? Let's say we work for a company, and they're like, all right, we hired you as our network engineer. We have a Class C address, and I need 7 subnets. And we're like, okay, work it out. I don't care how many hosts per subnet we have, but we just need to have 7 networks. Do it. So how do we do that? We have to find a way to where we have at least 7 networks or 7 subnetworks with this Class C address. So I'll show you how to create that subnet mask so we can get at least 7 networks, so it satisfies our requirement from our boss. So now that we know how to subnet, we know how to calculate those subnet IDs. A network administrator will be given a network ID, and it is your job to subnet it out based on a set of requirements, kind of like that, kind of like my example I just had. So let's say, again, we were given a Class C address. You can see right here. Let's say we were given this, and we were told we need to create a subnet mask that will provide at least 16 subnets. All right. Well, what are our steps? I wrote it out here so we could follow along, and I'm going to talk you through it. First step, identify the classful subnet mask. We will automatically know that based on the network ID that we are given. We are given a 201. What does that mean? Automatic class C. What is the default subnet mask for class C? /24. All right. Bam. We need to know that right off the bat. Now, next, we will start borrowing bits from the host field from left to right. So we start from the left side, and then we go right until it satisfies our need for networks. All right. So, all right, hear me out. Each bit borrowed will be plugged into a formula, 2 to the n. So this is like 2 to the exponent, 2 to whatever, however many bits we have. So we have all zeros in the subnet mask. Let's turn these zeros into ones, and this will give us a number of subnets. All right. So we have all zeros right here. Let's turn this into a 1. That gives us 2 networks. Turn on another one. We borrowed 2 bits, so 2 to the 2 now. That gives us 4. What is our requirements? We need 16. So keep borrowing bits. Turn on a third one. That gives us 8. Turn on a fourth one. That gives us 16. That actually fits our requirement perfectly. So, now that we were borrowing bits, what is our new subnet mask for that? You just add that up. We already know that the first 3 octets are 255.255.255. Now we have some 1s in the 4th octet. What does that mean? Just add that up. 128, 64, 32, 16. So 128 plus 64 is 192. 192 plus 32, 224 plus 16 plus 16, 240. That is our new subnet mask. Add that on to the original default subnet mask, and bam, we have just created a subnet mask that will give us 16 subnets. I think I jumped ahead of myself because I actually have a slide that explains this, so I'll help go along with you. So it said, so we borrow each bit and plug it into the formula until our requirements is satisfied. So I'll take it step by step. So again, remember what our requirements are. We need 16 subnets, and we are given a class C. Let's start with a /24, and let's keep borrowing bits until the formula is satisfied. So if we borrow 1 bit, /25, that's what it looks like in binary. That's how much it's plugged into the formula. That is how many subnets we get. Does not meet our requirements, so let's move on. Really have to do this. /26, we borrowed 2 bits, plug it into our formula, does not meet requirements. Moving on. /27, borrowed 3 bits, can only make 8 subnets, does not meet. Borrow 1 more. Notice it once we plug it into the formula, it equals 16 bits. Finally, this meets our requirement. Good. So, that is our answer. 255.255.255.240. This will give us 16 subnets with this class C address. All right. Now we have another formula just like this, but it goes on the opposite spectrum. What happens if we get a requirement to say, I need to have 14 hosts per subnet. I don't care how many subnets there are, but I need to have at least 14 hosts. So this brings us to my next example. To calculate host requirements, we do it in the same way, but instead of going from left to right, we are going right to left. and host bits are represented with zeros, right? Networking bits are 1, host bits are zeros. So we do the same thing. That is our Class C address that we are given, and our requirement is 14 hosts per subnet. So first step again, determine the class or the default subnet mask of that class. We know that it is a Class C, so it is a /24. We have 8 host bits to work with, all zeros. Now we start using bits from the host field from right to left to calculate the hosts. So we have a new formula, 2 to the h minus 2. Remember, calculating subnets was just 2 to the n meaning networking bits. Our new formula is 2 to the h minus 2. Why do you think that? Subnet ID and broadcast address. So we have to minus 2 to have usable host addresses. So again, we save our host bits and we apply that to our formula and it gives us our number. So let's move on to the next slide. Let me clear this off and we'll go through this. So again, simply keep borrowing bits until the formula satisfies the requirement. Remember, host bits are represented with zeros. All right, so we need 14 hosts with a 14 hosts with the Class C address. All right, so this one says let's start with all 32 bits used and work back to find how many bits we need. So if we save one host bit, we apply it to our formula, 2 to the 1 minus 2, or 1 bit used, it gives us 0 hosts. We cannot use that. If we have a /30, notice 2 bits being saved here gives us 2 hosts. Does not meet our requirements. If we borrow 3 bits, we have 2 to the 3rd minus 2. 6 hosts doesn't meet. If we have 4 bits used, or 4 bits saved, I should say, in the host, then that gives us 14 hosts per subnet. And this does meet our requirements, so our answer as well is 255.255.255.240, and that gives us 14 hosts per subnet. All right, it's just like calculating the subnets, but instead of going from left to right, we are going right to left, and host bits are represented with zeros. All right, host bits are always represented in zeros. Networking bits or subnet bits are always represented with ones. All right. Now, how do we find host addresses and broadcast IPs? Well, let me go through these, and after this is pretty much like subnetting on your own. So there are 4 addresses a network administrator needs to know to subnet. What is the subnet ID? What is the first available host IP address? What is the last available host IP address? And then what is the broadcast address? All right. So subnet ID or the network ID, however you like to call it. I like to say subnet ID because that means I'm talking about a specific subnet, not a classful address as a whole. So basically, it identifies the network. All right, that's it. It identifies the subnetwork. First host IP address is the first available address to be assigned to a host. So how do you get this address? Well, you find the subnet ID of it, which we know how to calculate those subnet IDs. You just add one IP address to it. That's it. That's the first available host address. So here's an example. If we were given the address 192.168.2.36/27, this is a host IP address that has been subnetted because this is a Class C, and this /27 means that we've gone beyond the classful boundary and stolen host bits or borrowed host bits to turn them into subnetworking bits. So based on this 27 here, we have a rotator of 32, right? So if we look at the fourth octet to make a /27, because remember, all other octets here have 8 bits in the subnet mask, and they're all turned on. I just wrote 8 out to make it easier. So those 3 bits, it does equal a /27, and this value right here, 128, 64, and then this last value is 32. That is our magic number. That is what we start rotating with, starting from 0. Then we go to 32. Then we go to 64. So this dot 36, it belongs to the 32 subnet. So that's how we get the subnet ID of a dot 32. All right, makes sense. Now, to find the first available host IP address, just add 1 to it. Bam, there it is. First host IP address. Simple, easy peasy, Japanesey. All right. Now, the next one, the last host IP address. This is a little bit trickier. It is the last available host IP address to be used for that subnet, and how we find that is to just find out what the original subnet ID is. So working with our original example, the first subnet ID, or the subnet ID for this IP address, was a .32. Find the next subnet ID, because remember we're rotating by 32 here because of that /27, is find the next subnet ID and then subtract 2 IP addresses from it. So our next subnet ID is a .64 minus 2, that equals a .62. And that is the last host IP address for the .32 network. All right. Now, there is another way too. You could find out what the broadcast IP address is and just subtract 1 from it. But that just means you have to know what the broadcast IP address is from the very beginning. If you don't know that, the easiest way, find the next subnet ID, subtract 2, and then that will give you the last host IP address. So the answer for that is .62. All right. Now this last one, the broadcast IP address, it is used to send data to all devices on the network. You may have heard this term broadcast domain. That is where a broadcast message will stay. It'll stay in this broadcast domain, and how people want to send messages to everybody on that network, they would send a message to this broadcast address, and every network has one. So yeah, so all binary ones in the host portion of the IP address. So if we actually break it down into binary, there will be all ones in the host field. That means that is the IP address. All devices must pay attention to this broadcast message, whether they want it or not. So that is one bad reason why we want to break down our huge Class A, Class B, and even Class C networks into smaller networks, so not everyone is sending broadcast messages out to each other. 2 classic examples of a broadcast message is an ARP request and a DHCP discover message, also a DHCP request message as well. So broadcast addresses cannot be used as an address for any device that is attached to the network. That's right. So if you were trying to apply an IP address to your host machine or to your router, it should spit up a message saying incorrect, cannot be used. All right. So broadcast IP address, it is the last IP address of the subnet. So the one way to find it, again, just like finding the last available host IP address, find the next subnet ID, subtract 1 IP address from it, and then bam, you found your broadcast address. So sticking with our example, bam, right there, we already know that the subnet ID is a .32. The next subnet ID is a .64 minus 1 IP address and that gives us our broadcast address for that network. All right, so 64 minus 1, well, dot 64, that equals a dot 63, and that is the broadcast address for subnet ID 32. Pretty easy, right? You're probably thinking like, no, what happened? So the good thing about these videos is that always go back and rewatch things. If you get stuck on something, just pause the video, rewind it, read the text, see if it makes sense. If not, message me, leave a comment, and I'll see if I could further explain it to you. All right. But the good thing about videos is you could rewatch them. All right. So with that being said, you can now complete exercises 4, 5, and 6. All right. So there is about, what? Do I have it? It's going to look something like this, if you could see it, where I'm just going to ask you certain things, and there'll be a column where you could put your answers. So, yeah. So I'll find a way to upload that, and then you can use it. And I hope these exercises will actually help you and get you in the rhythm of subnetting. Subnetting is very important, especially if you're going to stay in this networking career field or this networking field. You should know it like the back of your hand, and especially if you're going to be taking your CCNA exam, you should really nail down subnetting. It is one way to catch up on time because these Cisco tests, they're timed. And when you get a subnetting question, you should be able to figure out exactly what's going on with those IP addresses in like 30 seconds ish. They say about 30 seconds per subnetting question. And if you're spending like 5 minutes per subnetting question on the CCNA exam, and let's say they give you 10 subnetting questions, you wasted 50 minutes of a 90-minute exam. And there's also simulations on these Cisco exams, so try to really get efficient at subnetting so you could spend more time on the actual simulations for the test. All right. So let's put this all together. Let's assume that this is the uh, subnet mask for all of these addresses. Are these legal hosts? So this is where you have to put everything together, find out the subnet IDs, find out the rotating number, and find out if it is a subnet ID, a valid host address, or a broadcast address. So pause the video, do whatever you need to do if you want to um, uh, do this on your own, and I'll come back. So let me play some more 90s hip hop music for you. Y'all know me, still the same old. All right, not gonna listen to all of it, but let's get to it. So, first thing, is the .35 of this Class C address, is that a valid host? What happened here? Yes, it is. It is a valid host because the subnet ID for this address is, what's our rotator here? 64. So our rotator 64, and that means our subnet ID for this address right here. Subnet ID is a .0. So anything from 0 to 63, this subnet ID owns. So 35 is right in the middle of it, so it is a valid host address. What about the next one, .63? Is that a valid host address, or is that a address a host can use? No, it cannot, because that is a broadcast address. Like I mentioned here, 0 is the subnet ID, the last address is the broadcast address, BC, and you cannot use that. You could use anything basically from 1 to 62, at least in this range. So let's move on. .65, is that an available host address? Yes, it is. Because we're rotating by 64, 65 is the first available host address. What about 190? Is that available? Yes, it is. Because we're rotating by 64, so we go 0, 64, 128, 192, I believe, and then that should be it. So 190 is the last available host IP address. 191 cannot be used because that is a broadcast address for the 128 subnetwork. So this last one, 192, is that used for available hosts? No, you cannot. So that is the network ID for that Class C address with that subnet mask. So that cannot be used. Good, 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 good. You guys are going to be young subnetting wizards soon. Level 9000, hopefully. But, alright, let's see what else we got here. So, putting it all together again, let's say we have this address with this subnet mask. How many subnets are created by this mask? Ooh, so this is almost like a requirements one, but we are given an IP address, we are given a subnet mask. How many subnets are created with it, and then how many hosts per subnet. So this is a good one. So, like I said before, an IP address is like peas and carrots. There's the pea, there's the carrots. You can't have one without the other. If not, that's just a number. This is just a subnet mask. Doesn't mean anything. So, first thing with requirements, what was our first thing? Identify the class. What is the class? That's a class B. So, the default subnet mask ends right there. We have 255.192 that is used in the host field, but we turn them into ones. So what does that actually mean? Well, let's draw it out. 255 equals 8 bits. How many bits is that? 1, 2, 3, 4, 5, 6, 7, 8. How to create 192? 128 plus 64 equals 192, so that means we have 6 host bits. 1, 2, 3, 4, 5, 6. Alright, so remember what our formula was to find out how many subnets we have based on a certain amount of networking bits. 2 to the n, which equals 2 to the 8 plus 2 equals 10. So, what does that equal? If you're good with exponents, we already know that that is 1024. But one easy way on how to get there is all 8 bits. That equals 256 possibilities. Now, with every extra bit that is there, multiply that by 2. So, all 8 bits equals 256. Multiply, if we add another bit to it, let's say 9, multiply that by 2. 512. Add one more bit, 10. Guess what? 1024. And that is what 10 bits look like. 255.192, because we could see it in binary. So that is my answer for how many subnets are created with that mask based on that IP address. Now, what is or how many hosts per subnet? Well, remember our other formula, 2 to the h minus 2. H is represented with host bits. How many host bits did we have? Well, we had 6. 2 to the 6 minus 2. So what does that equal? How many bits does that mean? So this is 1, 2, 4, 8, 16, 32. No, I'm sorry, that's wrong. Let me go back. 1 bit has 2 possibilities. 2, 4, 8, 16, 32, 64. All right. I know you can't see that. That 6-bit right there, that equals 64. So that means it's 64 minus 2 equals 62 hosts per subnet. So that's my answer. 1024, 62. Let's see what we got here. Subnet's 1024, that's right. And then hosts are 62. Sweet. So we have actually subnetted. Now, that's awesome. Yeah. With this, with the knowledge that I just gave you in the slides in this video, you should be able to tackle any subnetting question now. It may take a little time, but remember everything that goes with the subnet mask, the rotator, what is the classful network, where do we start rotating, things like that. Just when you get to a subnetting question, just take a breath, breathe, and then go through the steps that I taught you. All right. Now this last portion that I'm going to go over, really, it does have to do with subnetting, but it does not, there's no pretty much subnetting involved. Well, there is subnetting involved. Never mind. Let me just get to it. VLSM, Variable Length Subnet Mask. If you have the ICD-1 book, you can go to this page right there for the Cisco Press books. It'll tell you a little bit more about VLSM. So VLSM occurs when an internetwork uses more than one mask for different subnets of a class A, B, or C. So what we were learning so far is how to calculate subnets with equal amount of hosts. But what happens if we want to conserve IP addresses and not waste host IP addresses when there's only going to be 2 hosts on that network, like point-to-point links? So the benefits allows engineers to better match the need for addresses with the size of each subnet, gives us flexibility, reduces the number of wasted IP addresses in a subnet. Coincidentally, that's also the disadvantage. More subnets mean that you have more IP addresses used for the subnet IDs and broadcast IPs. So it can have the flexibility to reduce the number of wasted IP addresses, but also just know every subnet that you create, you lose 2 IP addresses. So let's take a look at an example. So let's say we are given this topology right here, and we see these are the networks for or how many hosts per network. So we have 2 hosts here, 6 hosts here, 14, so on and so forth. So if we were given this topology and we're the network engineer and they're like, all right, we need a subnet mask that can fit everything in here. How does this work? So what we have to do is we have to look at our biggest subnet and say, all right, we need to give a subnet mask for our biggest subnetwork that we have. So we need 64 hosts. So how do we create a subnet mask for 64 hosts? Well, first of all, we need to know what we are given. Looks like we were given a Class C address right there, 192.168.10. So that means our default subnet mask is going to be a/24. So knowing what we know about our requirements for hosts, we need to find how many 0 bits in the subnet mask we have to make at least 60 hosts. So if we draw this out, 0 gives us a number of 2. Another 0 is 4, 8, 16, 32, 64. All right, so 2 to the h minus 2. If we have 6 bits, which equals 64 minus 2, that gives us 62 hosts per subnet. Bam, that matches. All right, so that means finish off the amount of bits in the subnet mask. That is a/26. We can give this portion of the network a/26. But if we kept every network a /26 for our class C network right here, that means we have we have 4 subnets. Well, we need more than just 2 subnets because there's 1, there's 2, there's 3, there's 4, there's 5, 6, and 7. We need 7 subnets. So we can't satisfy it. This is where VLSM comes into play. Give each network the amount of hosts they need and just give them the subnet mask. And then based on where everything lies, you need to do some shifting of these subnet masks. All right. So what I mean by that is, let me get to that. So for 60 hosts, we have a /26. Sweet. So biggest networks should start first. So notice this scheme here, the smaller subnet mask, which is the bigger network, starts at the very bottom. So we have 26, and we got 27, 28, and then 30, or 29, and then 30 is at the bottom. I'll explain all that in just a second. So biggest networks first. Then we move on to the next biggest network. So we have 30 hosts. So what kind of subnet mask do we need for 30 hosts? Start with 0, or let's start with our host bits, which are 0. So 2, 4, 8, 16, 32. 32 minus 2 equals 30. Matches perfectly. So we need 5 host bits in the host field of our subnet mask. So that means we have 3 bits left over equals 27. Now, one reason why you want to start with the highest or the biggest network and go smaller is when it comes to these network IDs or subnetwork IDs, they can only be placed in certain sections. All right. So what that being said is, if we're rotating by what's our rotator here? 32, I believe. 1, 2, 3, 128, 64, 32. So we're rotating by 32. If we have a /27, our subnet IDs have to land on a rotation of 32. So we have 0, 32, 64, 96, 128. Let's say we didn't do correct VLSM, and let's say we didn't even use this. We started with a 0 and went to a, so that took up IP addresses 0 through 63. So the next available subnet would be something that starts with a .64. Let's say we threw in a /30. /30 will give us 2 host IP address, which we'll use for these guys. And let's say we stuck it in right there. /30 takes up 4 IP addresses. So that means all the way, so the next subnet ID would be a .68. And let's say we just threw in a /30 right here. /30. We cannot put in a /27 right after this .68. Reason being is if we look at where our subnet ID lies, it will never land on a .68. All right, so that you'll just have IP address subnet overlap. So you have to carefully design your network, make sure it falls into this scheme of smaller subnet masks start at the bottom of your network, and then your let's say your /30s, which only have 2 hosts, 2 host IP addresses, but it takes up 4 addresses, 4 IPs. You start at the very bottom because nothing gets smaller than a /30. Normally you would use /30s for point-to-point links, and you're never going to have a network with just 1 host on it. So there are things like called host networks, but that's something totally different and beyond the scope of this video. But that is how VLSM works. Whatever the network is and how many hosts you need based on requirements, just give it that specific IP address. make sure it fits in this puzzle of IP addresses, because you have to remember what is the rotator of that network that it could fall on, and just kind of piece it in there. Fit it in where it needs to. And if you design your network properly, you'll have this chunk in here for growth. All right. So let's say another /28 comes into play. What is the rotator of a /28? 4 bits. I think the rotator's 16. I don't think 16 will ever lie on a .120. So the next available IP address for a rotation of 16 would have to be a 128. So you can start here, 128, and you'll have a little chunk here of another /29 that you can use, and then you just start inserting those subnets. All right. So that's all I have for you. If you guys have any questions, go ahead and leave a comment below. I enjoy doing this. I hope this was informative for you, and I'd like to thank you for viewing.